Have you ever just pictured a perfectly simple object? Like a sphere or maybe a donut.
Sure.
You know exactly what's inside and what's outside. It's obvious. But what if you tried to imagine a shape that completely defies that distinction?
Right.
A surface that's totally boundaryless but has no real inside or outside at all.
Then you'd be thinking about the Klein bottle.
Yeah.
It's a dive into a really strange and I think beautiful world.
Exactly.
It's one of those famous objects in topology. It was first described way back in 1882 by Felix Klein, and it's the classic example of what we call a non-orientable surface.
Non-orientable. What does that actually mean for someone trying to picture it?
Well, it just means you can't consistently define a direction on it. There's no permanent up or down. So if you were, say, a tiny traveler on its surface, you could walk a certain path and come back to where you started.
Okay.
But you'd be upside down.
Oh.
And you never crossed any edge or boundary to get there.
That idea alone just completely scrambles my 3D-oriented brain. So let's talk about the construction. How do you even begin to build something like that?
Conceptually, you start with a square piece of paper.
Right.
You take two opposite sides and glue them together. That gives you a cylinder, which is easy enough. The real challenge comes next.
Trying to glue the two open ends of the cylinder together.
Exactly.
Yeah.
But to make it a Klein bottle, the math says you have to glue them with a twist so the direction of the arrows matches. And to do that in our three-dimensional world,
You can't.
you're physically forced to punch one end through the side of the cylinder to connect it from the inside.
So those famous glass models, the beautiful ones you see in science museums, they have that self-intersection.
They do. And that brings up a really crucial distinction in topology. Those physical models are what we call an immersion in our 3D space. They self-intersect.
An immersion. Okay, so how is that different from what a mathematician would call an embedding? Why is that so important here?
An embedding is when a shape fits into a space without ever crossing itself. It's a perfect, uncompromised representation.
And the proper Klein bottle is supposed to be an embedding.
Yes. Mathematically, the true Klein bottle has zero self-intersections. But to achieve that, to get that perfect embedding, you have to conceptualize it in a four-dimensional space. We call it R4.
In the fourth dimension.
Think of it this way. If you draw a line on a flat sheet of paper so it crosses itself,
Yeah.
you can't uncross it in 2D. But if you lift one part of the line up into the third dimension, the intersection disappears.
So the fourth dimension is just the extra wiggle room the surface needs to use to curve around itself instead of crashing through itself.
That's a perfect way to put it. It avoids the collision entirely.
It's just a fantastic illustration of how mathematics can describe realities that are just, beyond what our eyes can see.
Absolutely. And, while it feels incredibly complex, it's directly related to a much simpler shape, one most people have actually played with.
The Mobius strip.
The Mobius.
What's so fascinating is the connection between them. A Mobius strip has that one-sidedness, but it also has an edge. It has a boundary.
Right, whereas the Klein bottle is what we call a closed manifold.
Meaning it has no edges, no boundary at all. It's complete.
Like a sphere or a torus, yes.
Yeah.
But here's the amazing part. If you take that closed Klein bottle and slice it right down its plane of symmetry, you don't get two simpler symmetrical halves.
What do you get?
You get two mirror image Mobius strips. One is left-handed and the other is right-handed. It's an incredibly elegant structure.
Understanding these kinds of complex, abstract relationships, especially when you're jumping into higher dimensions, it really shows how you sometimes need to leverage external expertise to see the whole picture.
Oh, for sure.
And speaking of that, this deep dive is sponsored by Embersilk. If you need help with AI training, automation, software development, or just figuring out where AI agents could make the biggest impact for you, Embersilk specializes in that. You can check them out at embersilk.com for all your AI needs.
The fact that we can even define and map these non-orientable surfaces, it just proves that our mathematical ingenuity really does outstrip the limits of our physical senses.
It does. We can understand structures we can never truly hold.
We can rigorously prove they exist.
That ability to map these complex, higher dimensional spaces is it's genuinely inspiring. And it makes you wonder, what are the implications for, say, cosmology?
That's a fascinating thought. Some theories, like the Alice universe concept, play with these non-orientable ideas.
So the very shape of the space we live in could have these subtle, counterintuitive properties. It just shows there are always new layers of the universe for us to discover.
Indeed, it's proof that there's always more to learn and more complexity to embrace.
Well, if this deep dive on RO challenged the way you see the world, make sure you subscribe so you don't miss our next analysis. Hey, and if you can, leave us a 5-star review. It really does help get the word out. Thanks for tuning in.